Hey there. I'm going to talk to you about breaking down natural language processing basics for SEOs and marketers and anyone else who's interested in understanding the basics of natural language processing. For those of you who don't know me, my name is Paul Shapiro. I am currently the technical SEO lead for Shopify. Okay, just to hammer this out, some assumptions and prerequisites for this presentation. I assume some familiarity with Python, some familiarity with some common data science libraries for Python, such as pandas and NumPy. You don't have to be an expert, but it's helpful if you have a good sense of those libraries. And also, for a lot of the examples, I'm going to be using Jupyter Notebooks. So familiarity with Jupyter Notebooks is helpful, but optional, because I'm showing them to you in Jupyter Notebooks. Doesn't actually require you to know anything about them. With that being said, there's all this prior knowledge required, but there's no prior knowledge of natural language processing itself required. Okay, so which libraries are we going to be using for examples? Here's the list right here. So we're going to be using the JSON package, pandas for tabular data, using re for regular expressions, NLTK as a standard natural language processing library, NumPy for some statistical computations, string, Spacey, which is another NLP library, SciPy, and a little bit of Matplotlib. And as much as I'm doing these examples in Python, I do want to point out that there is a low code option that I'm very fond of, which is the KNIME ETL. That's KNIME. It's got this great drag and drop interface with tons of NLP functions built right into it. It's very, very robust, and I highly recommend it if the Python is a little bit too much for you. Okay, so what is natural language processing, or NLP? The definition can kind of get a little bit more complex, but I think this is a simple enough one that, dots all the I's and crosses all the T's. NLP is a way for computers to analyze, understand, and derive meaning from human language in a smart and useful way. By utilizing NLP, or natural language processing, developers can organize and structure knowledge to perform tasks such as automatic summarization, translation, named entity recognition, relationship extraction, sentiment analysis, speech recognition, and topic segmentation. And obviously, there's a lot more than that. These are some examples. When it comes to NLP, there's sort of this old hat way of doing things and a new hat way of doing things. The old hat way of doing things relies on heuristics based on linguistics. So just common sets of rules that sort of make sense with language, and statistics. And actually, most of this presentation is going to be focusing on that because it's the foundation of NLP in general, but it is not the latest and greatest. And the newfound way of doing NLP is heavily reliant on machine learning. It's almost all machine learning. So for NLP, we're going to take an input, and that's going to be parsing some sort of semi-structured or completely unstructured text data. For example, there's a ton of basic NLP data sets available on GitHub if you're just looking to play around. So this is completely unstructured. We would use that text and we'd output it into something that's a little bit more manageable, and then try to derive some meaning from that text. Some other example data sources that you may want to look at, which are going to be things like digital books, ebooks, CSV data sets, Excel, JSON, XML, etc., Word documents, PDFs, and probably most relevant to SEOs and marketers, web pages. Okay, so let's use JSON as an example input. I found this JSON file of jokes. So we called it waka.json, and we're going to open that JSON file using the JSON library. And then we're going to convert that JSON file into a pandas data frame. So waka equals pd.dataframe, and we'll convert it from a dictionary into that data frame. And then we can use head to sort of output a sample of that data frame. And we see we have a body of a joke, some sort of category to which that joke belongs to according to the source of the data, an ID, and the title of that joke. Then we're going to do something called text preprocessing. So an example of that would be tokenization. So to do a lot of like the heuristical type NLP analyses for natural language understanding, text is going to need to be broken into units, which we'll call tokens. And they're usually units of individual words. So this pre-processing step is often needed to just sort of like parse, clean, and prepare text for the analysis, and we're going to convert that into a machine readable and interpretable format. This is just laying the groundwork for doing all of that. All right, so let's look at what tokenization actually looks like. So right here, we're creating a function we'll call tokenize words. And we're just going to use regular expressions to take these text blocks and convert them into individual tokens. So we'll take that data frame and we'll use a lambda function to tokenize those words using the function. And you'll see right here, so this joke body, what do you call a cat with no legs? Gets broken down into the individual tokens or individual words. What do you call a cow with no legs? And other text preprocessing concepts. There's preprocessing that's oriented around noise and junk removal or cleanup. So that's doing things like removing punctuation and special characters that just make things a little bit more confusing for analysis, removing things like stop words that, sometimes either add a lot more processing power to the work we're doing without much contextual meaning. Although that's changed a lot recently with a lot of like the more sophisticated NLP machine learning models. They actually like that language and it helps derive context, but for these simple models, sometimes it detracts. Common abbreviations, casing, etc. Okay, more examples. So let's convert everything to lowercase, so as not to think that a word that is starts with an uppercase is a different word that starts with a lowercase. So we'll create a little function to remove punctuation. And you'll see if we print out just that first joke in our data frame, what do you call a cow with no legs? Ground beef. All the casing is removed. So the capital W is now removed and replaced with a lowercase w. And let's do a little bit more. Let's not just tokenize, but let's remove stop words. So we have our little stop word removal function that is combined with some tokenization logic, put it to a data frame using a lambda function. And you can see the plain tokenized output is, what do you call a cow with no legs? But with stop words removed, it's just call cow legs ground beef. We may also want to expand common abbreviations. So for this example, we created a dictionary. So we have LOL mapped to laugh out loud, BRB mapped to be right back, SERP SERP mapped to search engine results page. Created a little function to expand our abbreviations. And then we remove some punctuation from a sentence like hold my beer while I check the SERP one moment, BRB. Once we run that through our abbreviation expansion, we see that turns into Hold my beer while I check the search engine results page one moment. Be right back. Okay, some more very important text preprocessing we may want to do is around the concept of just normalizing and standardizing text. Two of the most important concepts under that category are what we call stemming and lemmatization. Why do we do this? For one, it speeds up the machine learning analysis or even just more standard NLP practices. It speeds everything up, helps with disambiguation. So if we talk about disambiguation, let's just give an example. Since we're using jokes, say there are 500 jokes in our corpus. Corpus is a group of sort of a database of text that we're examining that mention the word United States. 25 of those jokes include the word economy, 15 include the word economic, and 10 mention mention the phrase world economies. Without any sort of standardization, those would look like three different concepts, even though they really have to do with the same thing. So it would produce three distinct co-occurrences along with United States. And we don't want that. We want the computer to understand that we're talking about the same thing. So we might standardize the word form. Okay, so let's talk about stemming and some of the pitfalls. So stemming is a more basic version of reducing the different form of a word to its base. It basically just chops off the end of the word to accomplish this, which makes it a very, very fast method, but it often results in words that aren't real. So just to give you an example, so we have four different words: study, studies, studied, and studying. If we perform stemming on that, we get studi with an I at the end, studi with an I at the end, studi with an I at the end, and studi at the end. They're all reduced to the same base, studi, but it's not a real word. That means nothing to a human who speaks English. So if we want to run stemming on our joke corpus, it would reduce it to this. So call cow legs ground beef becomes call cow leg ground beef. Or if we want to look at the next joke over, I think it's a little bit of a better example. What do you call a cow jumping over a barbed wire fence? With no stop words, call cow jumping barbed wire fence. But with stemming applied, call cow jump barb wire thank udder. A number of non-real words in there. There's also this other sort of more advanced process called lemmatization, but it also has its pitfalls. So it's a more sophisticated method of reducing different forms of the same word to a common base. It leverages a sort of predefined vocabulary and grammar to infer the root of a word. So in order to do that, we need to identify the parts of speech of each word in a sentence, which makes it much slower, but a more accurate method of reducing it to a base word. So let's look at an example. So we're using Spacey for this, which is a little bit faster, I believe, for lemmatization exercises. So we're loading a pre-trained model for lemmatization using Spacey and applying it with a function and lambda function. So those top two jokes become call cow leg ground beef. That's exactly the same as stemming. But if we look at the second example, which we look at the stemmed version was call cow jump barb wire thank udder. It's a little bit better. We create real words: call cow jump barbed wire fence udder. Did a little bit of a better job. So we may also want to just extract certain pieces of information and group things in a certain way. So in order to get more context. So that would be a concept of like n-grams. So we might group certain words together into, bigrams, which would be 2-word combinations, or trigrams, which would be 3-word combinations. We already briefly mentioned this, but like parts of speech tagging, is this word a noun or a verb? Chunking or chinking, which I think I'll get into a little bit later. Named entity recognition, is this word a person or a government entity or the name of a currency? Or even something a little bit more complex as word embeddings. So creating n-grams, we'll use NLTK for that. So we're importing NLTK. Same sort of format. We're creating our own custom function and piping that into a Lambda function. So we have bigrams and trigrams into our data frame. And you can see, what do you call a cat with no legs? Broken into bigrams would be what do and do you, and you call a. Trigrams are the 3-word version. So what do you call a, so on and so forth. Parts of speech tagging, we're going to use Spacey again, create a custom function, and then pipe that to a data frame using a Lambda function. And you'll see in this example right here, what is a pronoun, do verb, you pronoun, call verb. Everything gets broken down into this this combination of the word and the parts of speech. And you can visualize this pretty nicely using Spacey. So we're actually breaking this out with NLTK and then visualizing with Spacey. You can see these triples. So how they affect one another: pronoun verb, and here's the preposition, and it just helps for visualization if you're trying to understand this as a concept. Named entity recognition, I mentioned this. So we break down this joke, which Saddam Hussein is a person, Ireland country, Patty's the name of a person. We've converted that joke into named entities. I did just want to touch upon word embeddings and things like word2vec and glove vectors. This is sort of like the next step. Again, this is looking at the sentence as a whole. You're going to want to do a lot less of that removing and normalizing, because you want everything in its full context. So we're using GenSim to do word2vec. It's got some great models in there, and it's pretty cool. You can sort of see how things relate to another. So Germany in this corpus was highly related to Canada and Australia. Man was highly related to guy or woman or lady. You see how these words are very conceptually very similar. These are all countries. These are all things that have to do with gender, how you address people. And again, this is just pulling from the corpus. So that's within the context of that corpus of jokes. Okay, so using all these concepts, what we were going to do is create features to train our model on. So we're going to create these statistical models. We're going to leverage some personal heuristics. So we're going to think about these jokes and what might contribute to a more popular joke or a better received joke, and try to see if we could train a machine learning model to make a prediction on that. So we're going to use this data set that is from Reddit. We're going to break it out into the punchline, add which, because you think maybe the punchline might affect the interpretation of the joke separately from the actual joke body, the character count of the joke. If it's a longer joke, one could conceptually think like maybe it takes people a longer time to read it. They're more likely to react positively to it on Reddit. I created, is the joke profane or not? So I took a dictionary that someone posted on GitHub, a list of profane words, and ran all our jokes through that to indicate, just true or false, is this a dirty joke? So, and we wanted to go a step further, like how profane is the joke? So we counted, and again, this is a heuristic. The number of bad words appearing in a joke isn't necessarily an indication of how profane that joke is, but it was a heuristic. So it was one way of sort of assessing that. So we took the joke length and the count of bad words. Dirty count. These are not very dirty jokes. So once we have all these features created, it becomes necessary that we have to normalize them sometimes. So one way of doing that is doing something like a Box-Cox power transformation. It's just a way of creating, if you look at everything on a curve, to try to normalize, move things over a little bit, so that everything's on the same playing field. This is just how to do it mathematically, and think about it. You don't actually have to worry about this. The computer is going to do a lot of it for you, and we'll map it out graphically so you get a sense. So first we'll do this on the distribution of joke length, and we see what it looks like. It's slightly skewed to the left, but not bad compared to this one, which is very, very skewed to the left, which is the number of lines in a joke. Most jokes tend to be shorter. This is all over the place. This is sorry, actually, it attempted to make this more normalized, and the byproduct is something that's slightly more normal, but it's unfortunately all over the place, which is an indicator that like Box-Cox power transformation maybe isn't the best way to normalize this data. But you get it sort of moved everything more center to a normal distribution. And then we have to go through a process of vectorization. There's different ways of vectorizing this data. We're going to look at, you can do count vectorizer, n-gram vectorizer, and TF-IDF vectorizer very easily. So I'm just going to take this data, we're going to lemmatize it, removing stop words, so on and so forth, all that pretext processing that we were talking about. And then we're going to vectorize it just by count. And you can see vectorizing is just putting everything into a more machine readable format, numbers. And you can see that this is like basically the appearance of these words across the entire data set, and how they're counted across, and you're creating a multidimensional vector for it. We could also look at it in terms of word combinations. So, bigrams and trigrams in this case. So again, converting it into numbers. Then we're going to do TF-IDF, and I just want to stop for a moment and talk about TF-IDF because it's often misunderstood, and this is actually a great application for it. Whereas the count vectorizer looked at how many times a term or an n-gram appeared in a joke, and that would be represented as a positive integer. TF-IDF serves the function of scoring how many times a term appears in an individual joke, as well as how many times it appears across the entire corpus and database of jokes. With rare words would be deemed more important. That's a very loose understanding of it, but it's sort of easy way to conceptualize it. But more important because they're used to show how unique they are within the data set, making it more easy to distinguish one joke for another, essentially. Higher TF-IDF value is more uncommon, whereas a lower TF-IDF value is less common, actually. So we can use a TF-IDF vectorizer, and you can see that it's a decimal opposed to an integer value, which could be a little bit more useful. And we're going to apply these vectors to a decision tree model. This is just sort of a basic understanding of what a decision tree looks like. So you have, will sports team X win? We might look at different features like, are the player statistics favorable? Yes or no? Is the team they're playing historically better? So you'll break out all these different features, and it'll go through the different trees and say, like, given this combination of features, we think the outcome will be X or Y. Random forest takes that to a next level, basically combines a whole ton of decision trees and finds the best decision tree for that data set. And it's a basic type of machine learning. So we'll use sklearn as the model. We'll do a TF-IDF vectorizer on a number of the data sets, and we'll look at the features, and we'll output it all into the model, let sklearn run on it. And as we could sort of indicated by that Box-Cox transformation, this wasn't going to be a very good output. It's not very good at guessing whether a joke would receive a lot of upvotes on Reddit, because the data was very askew and hard to normalize using that method. But it's just to give you a concept of how it works. Definitely could have done this better. Could have done things to reduce overfitting and underfitting. Standardized features. I sort of did this thing where I mixed different types of vectors with sparse and non-sparse data. We could have leveraged those word embeddings and more advanced models like BERT or whatever to add more context to the jokes themselves, more sophisticated models. So that's sort of a high-level overview of natural language processing. I know this is a lot if you're unfamiliar, but I do recommend taking the time to try to understand it and go through these examples after you watch this, and I think you'll get a lot out of it. There's certainly more applications than sort of my crude example of using joke data. Could use it to better understand what is performant content. So I use joke data to say how many upvotes on Reddit would it receive, but we could do the similar thing with this content, perform better on search results, or this title perform better on search results, something like that. You could do things like predicting the natural link earning potential. There's this whole world of natural language generation. If you've played or heard of GPT-3, which can use to write bits of content. Semantic content optimization. You can use it to sort of infer semantic site architecture, design, and taxonomy, how one thing flows from another, user flow research, keyword research, etc. There's tons and tons of applications of NLP for SEO. At this point, you might be wondering, how do I learn more in general? This is a lot. There's so many great resources nowadays. Stanford has a free guide on their website, which is sort of like the de facto textbook almost on NLP. Kaggle, which is a machine learning competition website, has an amazing free resource for learning Python and data science applications with Python and machine learning. Towards Data Science is probably my favorite blog on NLP and data science. And then there's an awesome NLP GitHub repo with tons and tons of other resources. With that being said, I just want to say thank you. My name is Paul Shapiro. Enjoy the rest of the conference.